Right. So it's about time. 3:30. So I'll be the chair of this session, and today it is the emerging technologies and advanced characterization. So next we will have Dr. Zhang Yunhong, an associate professor of the Department of Applied Physics in PolyU. Dr. Zhang received his bachelor and PhD degrees in physics from Manchester University in 2010 and 2004 respectively. He is currently as an associate professor in applied physics at PolyU, where the main focus is on applied research and consultancy in applied physics, including laser, optoelectronics, mode locking laser development, laser application, solar energy conversion, and advanced materials laser photonic device development. His research interests cover topics including novel 2D materials and nanostructure used for optics and photonic devices, laser materials, high-power lasers, and novel materials for energy application. He has published over 172 SCI journal articles with an H index of 44 and total citations around 6,500 in Scopus. He was ranked in the top 2% of the world's most cited scientists in the field of optoelectronics and photonics by Stanford. Previously, he has completed several industrial projects as well, funded by companies including File Optronics, Huawei, Fenian, Asian, Halas Technology, Colgate, and Tissue Science Laboratory. And I'd like to invite Dr. Zhang to give his nice talk on this topic. Right, Dr. Zhang, please.
Thank you.
This interesting talk will be on the topic of high temperature and efficient solar steam generation using low dimension materials.
Can you see the slide, right?
Yep, it's working.
Okay, that's good. And
today,
yeah, thank you. Today I will talk about some of my research work that relating using solar energy to benefit the human being. So mainly using solar energy for sterilization and also freshwater generation. So since I become a researcher, I always have this statement stay in my mind: found the poor, sick, and needy, and serve them. So I always looking for opportunity in my research topic. I hopefully someday, it always a very, very lengthy journey to get your research to the journal publics. So I hope someday I can really achieve that. In fact, our society facing a lot of problems, and some people living in the underdeveloping country or developing country, they are actually having a completely different hospital environment compared to us. So as you can see from this picture, this is the autoclave we use in Hong Kong. So they are very expensive to own, and in order to operate them, it consume a lot of power, and they actually request uninterrupted power supplies. So Hong Kong have no such a problem because we always have a very steady and plentiful power supplies, right? But in some country like Bangladesh, Africa, you see they having a very basic facility in the hospital, as you can see from this photo. Some of them don't even have electricity supplies, or they suffer from a low shielding. That means sometimes they have electricity, sometimes they don't have electricity. Basically, the electricity is not enough for everyone at the same time. So that's why they suffer from low shielding. They basically cannot install or own the autoclave used in Hong Kong. So for emergency medical operation will be a problem for them. So here is the statistic we got from the web. So in fact, for surgical application, yeah, they really need to sterilizing the equipment carefully. So if we don't, have a facility to do this, then healthcare associated infection may happen. So For this problem, we will actually prolong the hospital staying of the patient. So they will cost a lot of money at the end, even more. And more deadly is it will rise the mortality rate of the newborn baby. So if the healthcare associated infection developed, then it actually increased 75% of the death rate of the infants. They can also increase the antibiotic resistance of the patient and dramatically increase healthcare system costs and patient suffering. So for this reason, we try to think of some idea, see if we can help them. Another problem we see is the water shortage. Again, yeah, we don't have this problem. In Hong Kong, we have a large facility. Water will be automatically transported to your household, for each household. But if you open up your eye, there's some water shortage problem, especially in the developing country. So here's a picture for refugee camp. They need to carry the clean water to their place. So Africa and India, they're using a lorry to transport the water if they need it. So in fact, some facility, low-cost facility, portable facility is very useful for some group of people in the world. So we can foresee that if we can develop some low-cost system, that will have a huge market, yeah, in the global. The conventional system have many problems. For example, like the reverse osmosis system, it's based on the membrane. They give a high pressure to the seawater and generate the fresh water, right? But in the meantime, each time they have to clean the membrane with fresh water. So to produce some drinking water, you need to consume some fresh water. So the whole process is expensive. You need a large infrastructure, and most important is you need energy to do this. So that's why we come up with the idea that can we actually use a solar energy driven a system which is low cost, efficient, and very quick to generate steam. So we believe that the world need a product like this. So very recently, some researchers developed a concept like localized heat. Solar evaporation is not new. In the past, you actually heat up some solar absorber, maybe the bottom of above water, and you're boiling the whole water to create steam, and that's how you can generate fresh water out of seawater. But for a structure like this, there's suffer from a huge heat loss. At the same time, it's not very energy efficient. Okay. Now we have developing some kind of concept like localized heat. Provided that if we can have a thin layer of material, they can absorb majority of the light. We only heat up the thin layer and evaporate a small amount of water, slowly, step by step. Then we can actually get rid of the solar concentrator. Once a system involving solar concentrator, we need a solar checker. So at the end, they make the whole system very expensive. Now, for this work, yeah, we implement using some very basic material like carbon nanotube, multi-wall carbon nanotube. This carbon nanotube is kind of a low-cost material compared to other form of carbon nanotube. And HFT too, kind of new two-dimensional material. And by bundle this material together, we found that this material can effectively evaporate water. The evaporation efficiency can up to 87%. So here are some of the characterization. We need a form that we use copper as a base material, And on top of this cover form, we deposit this carbon nanotube and also HFT2 on the top on the surface to make sure that they enhance the solar absorption. So the solar absorption increase up to close to 100%. This thing can be really dark at the end. So here's some kind of Raman spectrum to show that the material actually coated with this. Now here is some of the SEM picture and EDAX. Here is the piston copper form. You see there's a porous material. So why we need a porous material? Because at the end, this localized heat, although it happen on the surface, at the end, they need to have a water transport from the bottom to the upper surface to replace the evaporated water, right? So by we want this process to be automatically done with a capillary effect. So that's why in between we have this porous structure. So to make sure water can run the surface after coating, as you can see from picture B, yeah, it's quite uniform. It's uniformly coat on the surface of the copper form. In your right hand side of the PPT, you have the EDAX. EDAX show that the copper, carbon, C, HF, and TE are all uniformly coat on the surface. Okay, so you can actually see we found this element on the surface. So if we observe this material under HFTEM, you can see these multi-wall carbon nanotube coexist with the HFT2. And X-ray diffraction, you can see, these individual elements pattern, diffraction patterns. So you can see without HSP2, you have less characteristic peaks of this. Now, figure A actually telling us the mass change under the sun over time. Now, with pure water only, you see the mass drop. They will still be evaporating, but very slow speed. But if we put a copper form increase, the copper form with multi-wall carbon nanotube, the water loss increase, and we got the optimum, the best performance with both multi-wall carbon nanotube and HFT2 on the copper form. So picture B is actually showing us the performance in different light intensity. You may have a question, yeah. One sun, if you look at the literature, one sun is about 1 kilowatt, right? But why on earth we want to try 1, 2, 3, 4, 5? In fact, in some country like Bangladesh, sometimes in the daytime they can have a few more sun instead of one sun. So the intensity can be a lot higher in some country. So that's why we want to see the performance by changing the solar intensity. So figure C, you see that the evaporation rate are actually, the efficiency do not change too much, whether this is 1 kilowatt up to 5 kilowatts, increase slightly, maybe in 5 kilowatts. But evaporation rate actually have a linear relation with the sun intensity. So we also check, see whether the system can be operating many times. We actually try up to 50 cycles, and we found that the mass change rate are actually similar without too much degradation. So we found that after 53 cycles, we still be able to check, keep 1.37 kilometer per meter square per hours. So if you look at this figure, yeah, I can give you some rough estimation. Then the country house in Hong Kong, yeah, have 700 square meter, right, standard. So for this kind of rooftop, for fully operation, then they're enough to satisfy 3 or 4 adults for daily use. So I mean, the amount of water they evaporate is not trivial. So try to look at some data. Yeah, with only water, you see the temperature are quite uniform along the bottles. But with our material putting on the top, you see the bulk water underneath are actually cool. The temperature rise on the surface increase dramatically. So this is the feature of localized heat. Now, the surface temperature, as you can see from here, they can increase quite fast. 1,200 seconds, you can shoot, 100, maybe here is about 1,800 seconds, you can shoot around 77 degrees already. Okay, 77.5 degrees already. But without this material, then they can always keep around the room temperature, not much change. So it's quick heat. Quick heat is very important because one of the applications we're targeting is for sterilization, right? For emergency operation, we need to sterilizing the surgical equipment quickly. So this feature is very important. Now, more importantly, not only the surface temperature, is the steam they create. Can they actually have a high temperature steam? So here's the data. As you can see from here, under one sun, can easily get up to more than 65 degrees. Under the 65 degree, many bacteria will already be inactivate. Now with solar energy, solar irradiators up to 2 kilowatt per meter square, we can actually shoot the temperature up to 135 degrees Celsius. So in case there's a small, fluctuation of solar irradiation, you see that the temperature of steam generated is not huge. I mean, on and off, you see, on and off. You see there's running between 99 degrees to 133 degrees. So the conclusion is by using the material we fabricate, we can actually generate steam with temperature up to 135 degrees. So this is the first record that if you look at the literature for this type of research. To demonstrate the concept, we can really kill the bacteria or inactivate the bacteria. We choose E. coli. E. coli have longest, almost one of the longest inactivation time. That's the reason one. Another reason is this is E. coli is not very dangerous to us, right? So our laboratory can manage this bacteria. But if you look at the chart here, if you can inactivate E. coli, that means you can inactivate most of the bacteria you can find in the hospital. Now, here is the demonstration. You can see from the video. We have a solar stimulator on the top. Inside the card box we create, there's only a bottle with a breathing table, E. coli, and the steam are generating from the box there, the bottle there. Now here's the result. Before sterilization, you see many dots, column, bacterial colony site, many of them, okay? So after finish 15 minutes of sterilization, you see that dramatically reduce. 30 minutes sterilization, you only have one zone, okay? So we compare our result with WHO standard. We found that for the E. coli, we can satisfy the WHO standard. That's actually better than WHO standards, as you can see from there. So here's the calculation, the formula we use for calculation. So another proof of concept experiment we have done is we try to using some seawater we collect in the Hong Kong Bay. Yeah, our university next to a sea. We just collect some seawater sample outside. It's a natural seawater. Then we put a little bit of MB inside. MB is some kind of ink that serves as a pollutant inside the sea. So after the sterilization, evaporation, solar evaporation system, our solar evaporation system, we found that the salt are dramatically reduced. So it can also satisfy with the WHO standard. So below this line, then that means we can drink. I mean, only the sanity is safe to drink. So that was a before and after. We actually try with a different percentage of sanity. Now, the system we're proposing not only can be used in the developing country, but if we help install this system in the world, then it can also help carbon neutralization. So why is that? Because the commercial autoclave, they consume electricity energy, right? So first of all, it costs money to own and run. At the end, we make a estimation, for each run, each sterilization per liter capacity. So it's a 7.37 cents each time for the commercial available autoclave. Compared to our system using a solar-driven, power-up system, the cost can dramatically reduce to 0.21 cents. So it's a 35 times reduction. Okay, that annual lifetime cost also 30 times less. So if we have 10-liter commercial system, we can replace the 10-liter commercial system by our proposed sterilization system. We can actually cut the carbon emission 2.45 tons CO2 emission each year. That's equivalent to take off 3 gasoline passenger car off the road. Bear in mind that there's many hospital around the globe in a developing or underdeveloping country. So the impact can be huge when you add up the number together. So here is also another cost estimation, maintenance cost. There's a dramatical difference. So this slide is talking about the energy consumption. So we can also think about to operate our system with LED lamp. The idea was even in developing countries, sometimes some of the country in the equator, they have a plentiful sunshine, but of course this sunshine is not stable. Okay, so and also sometimes they have to, for emergency case, we are operating in the nighttime, right? Although majority of operation is happening in the daytimes with the sunshine. So what happens in the nighttime? We can actually have LED lamp. LED light is one of the energy efficient light source, can convert electricity to light energy up to 30-40% efficiency. So this light energy can be served as a light source to drive the sterilization system in the night time. So in this case, and there's a cost, right? The power cost. The power cost is also dramatically less compared to the commercial autoclave system and other solar evaporation source as well. So one of the advantage of our system is for cooling time, because we can surround the whole whole box with heat insulating material. Once you open it, then the system itself do not serve as a heat reservoir. So it's very easy to cool down. It takes only 1 minute to cool down. So this is also one of the important features for emergency operation. So another experiment we have done is using the waste material to generate fresh water. Okay, the idea was we try to test some of the material that we use every day. Very easy to find, very low cost. Sometimes they may be even a rubbish. It's a waste. We use the waste to do something useful. That is another attractive idea, right? So for this research work, yeah, one of my students recycled some of the carbon toner and the egg tray we use every day. This egg tray is actually made up of recycled paper, okay, and it's plentiful and no cost. So if you combine these two things together, intrinsically, egg tray are made of some kind of fabric, right? They have a plentiful of microchannel within. So supposedly, they should be able to transport water easily. Now, one of the problems for this egg tray is that they're not dark. That means they do not absorb too much sunlight. So by combining this dry toner together with egg tray, we should be able to make a very low cost solar evaporator. The egg tray will have two surfaces. One is rough surface, one is a smooth surface. So we also examine the performance for both sides. So by put some solvent, put the dry toner inside the isopropylene solvent, then we can spray this carbon material on top of the egg tray to make it dark. And after that, we have to dry them and oven them in a certain temperature. So bear in mind that the temperature is not high; it's only 100 degrees. 100 degrees is enough because the toner have a TG around 65 degrees. So we can very easily to integrate these two materials together with this low-cost techniques. We check the contact angle on both sides. We found that, in fact, the uncoated side will be more hydrophilic. So, but both of them can transmute water without problem, but one is actually better. And as you can see from there, this characterization, we can actually check, really got the peak of the relating material. So after the heat treatment, you see the two materials are completely integrated. Okay, so the penetration is actually deeper with a rough surface compared to the shallow surface. So after the treatment, you see the absorption dramatically increase up to close to 100% to ensure 100% of the solar energy being absorbed. So here there's some kind of characteristic index for the untreated. A is untreated and C is a treated egg tray. Laterally, this egg tray will have a mountain shape. And we found that this mountain shape will also have another advantage. So here is a diagram to show you the performance of rough surface and smooth surface. We found that this rough surface is slightly better than the smooth surface. Here, this diagram show you the performance in under the different sunlight, different intensity of sunlight. So one of the advantage of this mountain shape is when the sun is moving, when the sun, we don't have use a solar tracker, right? So when the sun is moving over the day, we found that the performance of a mountain shape does not change too much. So here, this diagram, you see, the efficiency can maintain compared to a completely flat surface. So we squeeze it to make the mountain shape to become surface and make a comparison. And we found that the 3-dimensional mountain shape is actually serve a better absorber than the flat shape. So another good feature we found from our system is we found some kind of a salt rejection property. So once we involve in the seawater, this salt sometimes will deposit on the surface and actually blocking the water transmission channel. But we found that our system will have some kind of a salt rejection performance. So after we done the experiment, we found that the water we produce is actually close to tap water. I would like to draw attention that in fact DI water is not suitable for drinking. Okay, we need some kind of mineral in the water. So the water we produce is actually better than the DI water. So here's some kind of experiment. So I think time is running out. More detail can be found in my publication, the free publication. Okay, this is the end of my presentation. Any question?
Thank you very much, Peter. It was a very nice presentation, particularly involving real-life application from fundamental studies. So the floor is open for questions. Do you have any questions to ask Dr. Zhang? Right, maybe let me start first. As I just realized, your real research interest is more on the translation from fundamental science to applications. What is the biggest hurdle from the translation of knowledge transfer?
Yeah, the whole process is actually quite lengthy. So we have already done the first demonstration. You see all these slides data can satisfy the WHO standard and things like that, right? But we didn't put it in clinical trial. For medical application, they need to have clinical data before the manufacturer or the company willing to pick it up. So that's why the second stage is we need some more resources, and we need to work with the hospital, for example, to persuade them, convince them our system is useful, and so that they can be our research partner. Because without the real support, yeah, it's difficult to finish the clinical trial. And
so finding the people, finding the collaborators is more difficult than the cost itself.
Yeah, and
or the investor.
You also no. This is the data you give it to the investor before
Okay.
you can attract the investment. You see, because they need to see the clinical trial. Clinical trial means that in the real life hospital environment, it's really work. In the laboratory stage, you have a solar stimulator and things like that. They won't believe you. Okay, so the next stage is the clinical trial. The clinical trial that involves hospital peoples and things like that. We actually contact with several hospitals in Bangladesh. Yeah, they are quite happy to support our projects. So the next stage is another funding application. Because at the end you need manpower resources to do this experiment, right? So in the hospital.
Is it easier to do it in Bangladesh or is it easier to do it in Hong Kong because of the local logistics or communication?
Yes, I mean in Hong Kong, of course, they will have advantage, but in Hong Kong they don't have these leads. You see, you talk to the hospitals, and we have a very nice autoclave, and although it's expensive, but they can afford it, right? So
yeah,
they not be so interested. So that's why our interest moved to the developing country, and they see the reason behind, and they feel more happy to help. So that's why we try to connect with the hospital in the developing country. We never tried with the local hospital. They might have interest as well, but we didn't try yet. Yeah.
Okay, so I'm just wondering about credential, this type of concern. Okay, thank you very much. Thank you very much.
Okay.
Any other questions from the audience?
Okay, I have a question. Hi, Peter.
Hi.
In your desalination experiment, and you have shown that when you increase the solar power concentration, right, you get a more evaporation of the water. So
yeah,
it seems the amount of water evaporation is not linearly dependent on the solar concentration. That means when you increase the solar concentration, actually you get more. I mean the average.
You got more solar. You got more solar energy. Then of course you have a more evaporated water. Yeah.
There is a slide.
But the efficiency are pretty much the same in terms of efficiency.
Really?
In input and output. They have a which slide, you know?
But I saw here. It seems it is more efficient if you use higher solar concentration, right? If you see 5 kilowatt, look at the picture B, right?
Yep.
The average is about 2 per kilogram. But if you look at the 1 kilogram case, it seems
there's a 10% change. Yeah.
Okay.
One sun to 5 sun there.
Yeah, from one sun
87%, but 5 sun is 91%.
Okay.
Yeah.
So the more concentrated solar power is more efficient, right?
Yeah. That was the case. Maybe due to less heat loss. We don't know the reason.
And another question is during the desalination experiment, do you find any solid sodium chloride deposit on your material? When you evaporate the water, right? The sodium chloride will be left in the seawater, and if the concentration is too high, then it will probably be deposited on the material and block the channel for water conduction. Do you observe this kind of?
For this material, we don't see material deposit on the surface.
Yeah, it depends. Depends on how long you do the experiment. The time is long enough, right? I suspect you have a very high concentration of the sodium chloride left in the channel of the porous channel of your material.
Yeah. This is a good question. Yeah. They will have a salt rejection feature. Of course, yeah, we cannot let the salt concentration getting higher, because that will also affect the performance. If you have a high concentration of salt, yeah, the salt will absorb water. You see, they will not. They will actually degrade the performance. So that's why in the real life application, we use some water, seawater. Let them evaporate down to certain concentration. We have to change the water. Let the water going back to sea and then
so you have to flush.
Yeah. Okay. Yeah. So for this material, because today I'm going to present 3 pieces of work there. For this HFT2, we don't see any salt deposition. But for in other works, HA, in the HA work, yeah, you can actually see some salt deposition on the surface. But surprisingly, it will disappear like this one. Yeah, 1 minute you see a bit of a salt there. Maybe at the beginning it's a bit dry on the surface. It dry up. Then one hour later, 3 hours, 5 hours later, and the salt is gone. I think they dissolve. They're going back to the seawater underneath again. So there was some kind of salt rejection feature. This is a big issue. We also investigate that the work is not published yet. With some plant, yeah, if they have a bigger channel run through the plant, that big channel will allow the salt going back to the water. The salt rejection experiment under process for other material. Yeah, we're focusing on electro material, low cost material can be easily to find, and so they will have a better chance for commercialization or go to the real life application.
Okay, thank you.
Okay, thank you very much. Any other question? We have 1 more minute. Okay, fair enough. Maybe let's move on to our next speaker. That will be Professor Huang anyway.
All right, thank you. Bye-bye.
Thank you very much, Peter. Thank you very much. So let me quickly share my screen.